Section 2.2. Describing sets. And sets is one of those tricky things in mathematics. What does it mean to be a set? We might say a set is a group of things. Okay. Sometimes when I look up a definition, I look at a word in that definition, and I'm like, what does that mean? So like, how would I define group? It's a group. Group is a collection of things, maybe. Okay. I don't know. I think I liked group better. What's collection mean? A set of things? There's some words and ideas that are so basic that I just got to show you what it is, and we all just get used to that idea, right? So what's a set? This could be a set. This could be a set. This could be a set. It doesn't really matter whether I call it a set, a group, or a collection. They're just different words to describe the same thing. Ultimately, I have to show you. I could show you a set of chairs. I could show you a set of people, a set of flowers, a set of rocks. Sets should be well defined. What that means is I can tell you what is in the set and what's not in the set. So for example, I could describe a set in a few different ways. I could just do something like this in words. Make a statement that describes a group of things, a collection of things, and we all agree like, oh yeah, I know what those are. Based on that description, we can make a list. When we're talking about sets, usually the list is going to go in curly brackets. And then we start listing them out. So vowels in the English alphabet, okay, A, B, C, oh wait, some of those aren't vowels. Let's see, am I sure about that? B a vowel? What's the next vowel? E?
I, A-E-I.
A-E-I, that's my fancy I there. O, U, ooh, that's not a U. U, sometimes Y, oh. And it turns out sometimes W can be considered a vowel, depends on how it's used. Typically, we're used to those right there. Now, how many people knew about the sometimes Y? You know that? Yeah, so sometimes Y is a vowel. Like, for example, my name is Gary, and the Y makes an E sound, so it's a vowel there. But in the word yellow, it's making it's not a vowel sound. It's a different kind of sound. So, and I think vowels are based on the way we use our mouth. So if your tongue makes contact, I think, or your lips make contact, then it's considered a consonant, and if they don't, it's considered a vowel, is my recollection. So in that case, yellow is not, and then Y is not, and then there's some people that spell Gary with an EY. And then the question there is, well, what's making the E sound in Gary there? Is it E or the Y or both? So sometimes things are complicated, is my point there. So depending on our experience, sometimes it can be hard to agree on what's in the set and what's not in the set. Okay. The W thing I just learned this year when I was working on some programming thing, and somebody said, oh, Y sometimes. So I had to write rules for when Y is on a computer program and when it wasn't. And then somebody said, well, W is sometimes. And they gave me an example. I forget what the example was, but it was like 1 in a billion words. All right. Point. A set should be well defined. Let's do one that's a little bit easier. Even digits. I would like you to list what you think the even digits are. Another set, even numbers. Write down what you think the even numbers are. Actually, I'm going to be a little more specific on the second one. I'm going to say even whole numbers. Oh, is this a trick question? You guys are looking at each other. What the hell is he talking about? Whole numbers. Anybody remember what a whole number is? Counting numbers? How about counting numbers? What's the first counting number? Yeah, 1, because you count, like I go, how many people are in the room? 1, 2, 3, 4. So the first counting number is 1. Whole numbers include counting numbers plus 0. Okay. So even whole numbers is 0. 0 is a whole number. 0 even? What's it mean for a number to be even?
It goes into it equally.
What goes into it equally?
Um,
2.
2.
2 goes into it equally, yeah. If 2 goes into a number with no remainder, it's called even. That's how we say even. And if you take 2 into 0, 2 goes into 0 0 times, no remainder, 0 is even. Yeah, so the first even whole number is 0. The next one is 2. Next one is 4, 6, 8, 10. That's a whole number. 12 is a whole number. What's the biggest one? A million? A million and 2? A million and 4? No, a billion. A billion and 2? A billion and 4? This goes on forever. Dot, dot, dot. Digits. A digit is a single character. 10 is made up of 2 digits. It is not a single digit. So the even digits are 0, 2, 4, 6, and 8. That's it. How many even digits are there? There are 5 of them. So my point is a couple of things here. One, well-defined depends on our knowledge of the definition, right? So even we kind of know what even is, but we had to be reminded a little bit more clearly. And then digit versus whole number, subtle but important distinction. Digit is a single character. Whole numbers can be made up of multiple digits. Like 12 has 2 digits in there, 10 has 2 digits in there. Okay. So that's part of it. The idea of well-defined means we have to understand the definition. And two, some sets have a finite number of things. I can count them and tell you how many there are. But some go on forever. So this set right here is an infinite set. Whereas this set up here is finite. My main focus in this section in the books is finite sets. Rarely will we go with sets that go on forever, because the important thing for me in this section with sets is the question, how many? How many are in that set? When we ask the question, how many are in a set, that's the idea called cardinality. Cardinality, there we go. And you may have heard of cardinal numbers versus ordinal numbers. So cardinal numbers are like 1, 2, 3, 4, 5. Ordinal numbers are like first, second, third, fourth, fifth. Two slightly different ideas. When I count people, it doesn't matter the order I count them. But if I was sorting you by like last name, then there's a first person and a second person and a third person and so on. So that's ordinal, order. Cardinal means count. Who cares? So if you want to be an elementary school teacher, you should care. And here's just a simple reason why. I would like you to do your best to write something on a piece of paper to answer that question. What does 3 mean? It's almost as hard as what does the word set mean? What does 3 mean? And you may think back to like high school or elementary school when you define something, you're not supposed to use the word in the definition. So I can't say it means I have 3 things. I can't use the word in the definition. So to tell me what 3 means, you can't use the word 3. Because I want to know what 3 means. You can't just tell me it means 3. I don't know what 3 means. Speak a different language. I know a lot of words in English, but I don't know what 1 means or 2 means or 3 means or 4 means or 5 means. How would you explain that to me? It's easy to write down, or is this feeling really painful? Yeah. So I mentioned earlier with sets, it's hard for me to explain. Like if you don't know what the word set means, and you don't know what the word group means, and you don't know what the word collection means, I have to show you. And that's bottom line, what we have to do with 3. It means this many. How many? That many. Or that many. Or maybe I hold up 3 fingers. Or maybe I show somebody 3 marbles, or 3 coins, or 3 markers, 3 people, 3 chairs. I got to show them that many things. That's what 3 means. And it doesn't matter whether I write it as THREE or I use the numeral like that. It's this many. And I just show lots of examples of that many. Have you ever known kids that learn to count? When they're really young, they go 1, 2, 3, 7, 8, apple. Like they don't quite. I remember my kid got up to 5, and I'm like, yeah, what's next? 1, 2, 3. And they start over. It's like, oh, we don't got it yet. Right? It's something you learn by experience. It's that many things. So the point of looking at sets is ultimately our idea of numbers comes from us observing 3 things over and over again, and which is we call it 3. That many things is called 3. If I hold up 2 fingers, that many things is called 2. And I can show you 2 of this and 2 of that and 2 of something else. And eventually you're like, oh yeah, 2. I get 2 now. It's that many. And that's the idea of, again, we see groups of things all around us, and we've learned to count things. Like if a small child has 3 toys and you take one away, are they going to notice? Before they can even count 3. They will. They will totally notice. A nursing baby learns there are 2 breaths, and if they only get one, they know they missed the other one. There are studies. Infants can count. 2, 3. They notice these things. Birds can count. There are studies on that too. It's kind of wild. Do birds have language like we do? Not that we know of, but they can still differentiate between 1, 2, 3, 4, up to 5. I think some birds can count higher, but they count in a different way than we do. But they can recognize the difference between 4 and 5, which is kind of cool. And it's all based on this idea, groups of things, and counting how many are in there, doesn't matter what you call them. All right, with that in mind comes another idea, a one-to-one correspondence. One-to-one correspondence relates to sets of the same size. So I could have set A, and set A has a 1's digit and a 2 digit and a 3 digit. And set B has an X in it, a Y in it, and a Z in it. And a one-to-one correspondence means for every element in one set, I can connect it to an element in the other set and not miss anything. And there's lots of ways I could make that happen. The easiest way is to just connect them in order. So if we want to connect a one-to-one correspondence, means you can connect the elements in one set to the set elements of another set, and you account for all elements in both sets. So for example, I could say, all right, 1 will connect to Z, that's that correspondence. 2 will connect to Y, that's that correspondence. And then 3 can connect to Z. Did I miss anything in A? Did I miss anything in B? The answer is no. So there is a one-to-one correspondence between those 2 sets. That's the idea of sets of the same size. And when we're very young, we get used to that idea, and then we get used to names like 3 and 4 and 5. Now, I could have connected them some other way. Or alternatively, I could have taken the set 1, 2, 3 and the set A, no, not ABC, I'm using X, Y, Z this time. X, Y, Z. And I could have said, well, let's let 1 connect to Y, and 2, you can connect to X, and 3 you connect to Z, and I'm still okay. The order doesn't matter. It just matters that there's a connection from an element in one set to an element in the other set, and I got to account for all of them. Suppose I had the set 2, 4, 6, 8, and A, B, C. And we decided we want to start with the 8 maybe. So I could say 8, you correspond to C. C is taken, so it can't be used again. 6, you can connect to B. And 4, you can connect to A. 2, sorry, I don't have anyone left. So that's not a 1-1-1 correspondence. And usually I'll abbreviate that as a 1-1. So 1-to-1 correspondence means the sets are the same size. We can match up perfectly and not miss anything. And this idea works great with finite sets. With infinite sets, it gets weird. I don't want to go there. We're not going to do too much with infinite sets. All right, some set notation. This says 2 is an element of that set above. So that little funky E-like symbol just means is an element of or is in. Three is not in that set. So that's the shorthand for that. Just the E for element of, but a line through it. Notice I wrote it as 4, 2, 6, 8 instead of 2, 4, 6, 8. The order you write things doesn't matter. So this set here is the same or equal to, oops, equal to the set 2, 4, 6, 8. Or we could call the set 8, 6, or 2. Order doesn't matter when we list a set. What you don't do in a set is repeat elements. So just note on that with sets, order of elements doesn't matter. Just don't repeat elements. So I could have a set, that's the set of letters in the word mathematics. We could write that as a list. And And there's lots of ways to write the list. I could start listing them out as I see them. There's an M. We always separate them with commas. There's an A, comma. There's a T. There's an H. There's an E. There's another M. I don't need to write it again. There's another A. Don't write it again. There's another T. I already wrote down T. There's an I. Did I list I yet? Nope. There's a C. I don't think I listed C yet. And there's an S. Oops. Too many scribbles there. And then close it once you're done. So we usually put sets in curly brackets. Again, order doesn't matter, but what does matter is you don't list things more than once. That's redundant and unnecessary. And I could put them in alphabetical order, right? I might ask myself, like thinking about all the letters in the alphabet, is there an A? Yes. Is there a B? No. A C? Yes. A D? No. An E? Yes. F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T. I think I'm done. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So those are in alphabetical order. Same set. Only list the elements once. Order doesn't matter. Subsets. So subsets are also sets. So for example, vowels in mathematics would be A, E, and I. And that right there is a subset of M, A, T, H, E, I, C, S. Vowels in the word mathematics are a subset of all the letters in the word mathematics. Anybody know what the most common letter in the English language is? The letter E. A set can just have one thing in it. So the set with just an E in it is a subset of the letters in mathematics. And I mentioned earlier, sets are important because counting sets is where our numbers come from. That's how we learned to count early on in our lives. So I can have a set with one thing in it, 3 things in it, 8 things in it, 10 things in it, 100 things in it. You can also have a set with nothing in it. It's called the empty set. I like to draw it as an empty set of brackets. Sometimes it's looks like a 0 or an O with a big line through it like that. Either of these is the empty set. And this is a weird but important thing about set theory is the empty set is always a subset of any set. And in this section on sets, there's 2 really hard questions that I'm not going to answer right now. I want you to think about a little bit and read about in the book. And I've got a video about them you can look at later. And those are, one hard question is how many subsets, oops, does a given set have? And it turns out there's a pattern to that. So if you say there's 10 elements in this set, I can tell you exactly how many subsets there are. If you say there's 5 elements in the set, I can tell you exactly how many subsets there are. There's a pattern to that. And that's one of the problems you're going to read about in the book. The other interesting and challenging problem in the book related to sets is how many one-to-one correspondences can there be? And I'm not going to answer these right now. I want you to think about it when you read in the book. Oh, how did that happen? That was interesting. How did that happen? All right, so those are all the big ideas I wanted to go over in this section. Next, I want to just do a quick view at what the activity for sets is. And it's something you can get started with what you know now, but you can't finish it until we do some stuff next Monday together. Because the activity involves section 2.2 and 2.3. But I posted it this week, but it's not due this week. If I did the due dates right. Let's hope. Look at that next, and we're done.